Hi everyone, my name is Aaron Paddy, a computer science undergrad at Grambling State University. And this summer, I worked with Dr. Mario Harper, a professor at Utah State University, on digital twin emulation of electrified roadway pilots. Now, why dynamic wireless power transfer? So, current EV infrastructure presents critical limitations such as charging requiring being stationary and also extended dwell times and creation of range anxiety for long distance transport. So dynamic wireless power transfer enables continuous charging of electric vehicles whilst in motion. Now, DWPT code fundamentally redefine EV infrastructures, but then it requires comprehensive testing in realistic operational environment. So that's basically what I'm doing. My research objectives basically is about developing a flexible digital twin architecture for dynamic wireless power transfer system and also enable comprehensive analysis of design parameters and providing a foundation for iterative hypothesis testing without physical infrastructure development costs. So basically, developing a simulation framework for dynamic wireless power transfer in electric vehicles. Now, to start, I modeled a portion of Salt Lake City. So that's my digital twin environment architecture. Picked sections of Salt Lake City and integrated those sections using OpenStreetMap, and we were able to import those coordinates into Blender, where in Blender we used the Create Road Mesh add-on to create road meshes that mimic actual urban environment in Salt Lake City. After that, we were able to export these road meshes into color to simulate it and form that 3D mesh that we actually need. So the system architecture of my software basically is in three stages. We have the control interface where we use Xbox controller for input handling. That means to control our vehicle in the simulation setup. And then we have the simulation core. That's basically about the processing layer, how we're able to input our OpenStreet data map into our Blender and form the 3D mesh of a city, and then imported those mesh into the color simulator to generate the world, and also have charger placement script be able to design our vehicles and track battery state. Then we have the output layer where we're able to visualize the charging efficiency of the batteries whilst on the chargers. Now, how were we able to set up our charges in our simulation system? We use coordinate-based placement. That means we're able to extract precise core coordinates from Blender mesh data to ensure alignment with the road surface. And then we pass these extracted data into a Python automation script and spawn the charging infrastructure on our roads in our simulation system. Now we're able to create mimic actual Kenworth semi trucks that are currently being used to test dynamic wireless power transfer in Utah State by using real-time Xbox controller interface to enable precise vehicle positioning and movement over these charging infrastructures. And we are also able to integrate this with wireless charging receiver systems that can mimic actual receiver electric vehicles that can interact with these wireless chargers. Now, this is basically a summary of what we did. So for the road construction, you can see this is a map of Salt Lake City, and this is the portion that we rendered in our color. So this is how the map looks like in our color environment. And that is our charger installation. So as you can see, this is just a model of wireless chargers, and we wanted to replicate this in our simulation system. So this is basically how the chargers looks like in our simulation system. And Kenworth semi trucks currently at the engineering laboratory at Utah State. We were able to model them to mimic the actual Kenworth trucks. So here you can see these are the trucks that are being moved on our wireless chargers, and you can see the interaction between the embedded charging coil and the inductive receivers under these trucks to mimic actual vehicle charging. So this is basically a video representation of what I did. So here you can see our vehicle moving along the road, and you can see the navigation panel which shows the details of the vehicle, the direction, and also the battery percentage, which is currently 79.4. You can see the chargers, which are the rectangular green boxes on the roads. So those are the chargers. Now, as the vehicle starts moving on the chargers, you can notice the battery percentage increasing slowly. If you check the notification or the navigation tab that shows the analysis of the vehicle and the charger, you can see it's increasingly slowly as the vehicle moves over the chargers. Yeah, so that's a video representation of what I actually did. Now, what are the next steps in future research direction? So currently we are uh, implementing autonomous vehicle navigation to move on these roads for optimal charging trajectory planning and execution instead of manual controlling of these vehicles. And also we aim to employ machine learning optimization strategies for dynamic driving behavior adaptation and energy harvesting maximization. And also we have scale expansion to broaden the simulation scope to encompass metropolitan scale and multi-vehicle interaction to mimic actual multi-vehicle traffic on roads. So our final thoughts, we built the modular dynamic wireless power transfer testing platform in Carla, and it supports flexible charger or vehicle setups, contributes to an open-ended tool for future city planning and dynamic wireless power transfer research. So dynamic wire power transfer research needed some flexibility, and we hope that our simulation system is able to meet that flexibility. So acknowledgement, I'd like to thank the Aspire 2025 research experience for undergrad students at Utah State and also NSF, and also special thanks to my mentor, Dr. Mario Harper, for his assistance and support, and also the Aspire Research Center for their guidance and resources. Thank you very much for having time for my presentation.